Recording?
Yeah, great. Thank you.
Thanks.
Hey, Warren, I might lose connection here, but do you mind introducing Ramesh? And I made him
Yeah,
host, so everything should be good. Maybe give him like a couple more minutes. Folks seem to be trickling in.
you're muted. What?
Not at all.
Yeah. So, yeah, I don't need, I mean, in fact, I can start off and you don't even need to introduce. So, yeah, either way is fine.
Very good. Yeah, let me introduce the. Hi, everyone. This is Warren Savage. I'd like to introduce our first of our lecture series from the Cryptolets team. Joining us today is Dr. Ramesh Karri. And Ramesh, you can introduce yourself and the topic we're talking about today.
Thank you, Warren. Hi, I'm a professor of electrical and computer engineering here at NYU. And thanks for joining. And thanks for having me as the first speaker on this Cryptolets speaker series. The title of my presentation is, I think the one that I shared is LLM for PQC, but I wanted to give you a bigger picture of where we started off on PQC sometime a few years ago, and then go through agentic approaches to HLS and tie this up into the LLM for PQC ongoing effort and LLM for secure PQC. That's the map for my presentation today. Uh, uh, so circa, I think this was something that we, I think view, admit. Sorry, I'm admitting people. We can do that. Uh, okay, good. I think in 2016 or 17 is when the post-quantum cryptography standardization started. And this was a quote from Daniel Epon, who was at NIST at that point in time, and leading or was part of the group that was leading the standardization effort. Uh, so quickly, roughly, current public key crypto systems, RSA, Diffie-Hellman, and even ECC, they all rely on strong mathematical problems that are difficult for classical computers to solve. These include, for example, integer factorization, and also discrete logs. But in 1994, the Professor Peter Shor showed that if you have a sufficiently powerful quantum computer, one could solve these problems quickly. So this presents a problem. The problem is, from an attack as an adversary, you can harvest all the encrypted data today, and you can then hold it back and break it once a suitably powerful quantum computer becomes available. So the only defense or a reasonable defense is to transition into these quantum resistant algorithms now, which was about a decade ago is when this effort started. So that was the rationale for this NIST standardization process. So in 2016, NIST initiated this global process to solicit, evaluate, understand, and standardize quantum resistant public key cryptographic algorithms. This was similar to the process that they used when they did the private key algorithms that was circa 98, 99, and the outcome of which was an advanced encryption standard, AES. So this was a multi-year competition then, and it is a multi-year competition now. So that it also takes multiple years of the cryptographers have time to conduct rigorous attacks, study the algorithms, and then make sure that they're secure. And once you do that, make sure that these are easily implementable in software and easily implementable in hardware. So that was the NIST PQC, or the standardization, cryptographic standardization process in general. So this process started off sometime in late December, in late 2017. About 70 submissions came in, and after about a year and change, uh, 26 candidates advanced into the second round, and 9 of them were one kind of algorithm. These are called the digital signatures. And then at that point in time, they expected the standardization to finish up in 2022, and it probably might have happened at about that time, a little later. And if you look at the round two digital signature candidates, here I'm summarizing them. You have 3 classes of algorithms for digital signatures. Uh, 3 of them are in the lattice-based cryptography. Uh, 4 of them are based on multivariate cryptography, and hash-based are 2 of them, Picnic and Sphinx. So as the process moved forward, one of the things that at some point in time, the initial rounds were mostly to study the security of these algorithms. So circa 2021 or 2019, late 2019, 2021, during peak COVID, uh, the hardware challenge arose. How do you make sure that which of these algorithms are easily implementable in hardware? And what are the power, performance, and area trade-offs? And to do this, now imagine you have, on a short time scale, there are 9, but overall about 26 algorithms. So the bottleneck for a traditional hardware design methodology is to make sure that all the algorithms are rewritten in Verilog or VHDL, your favorite language. Some of you might even like Chisel. But this process is a bottleneck because it's slow, because it's a manual process, and it requires expert engineers. And the problem is that it's not just that these engineers are experts in digital design, they should also be experts in cryptography. So creating handcrafted designs for even 9 complex PQC algorithms is time consuming and difficult. And so what we did was come up with a common framework to fill this gap. And what we did is to propose using high-level synthesis as a methodology. Okay. So as I said, we said, let's start with high-level synthesis design flow. And what we did there is we came up with a uniform design methodology that uses, instead of Verilog or VHDL, RTL, handcrafted RTL, to start with this reference C code that all these participants submitted to the NIST competition. Let me admit. There's one more. Yeah. So this way, instead of handcrafting RTL, you could potentially take the C code and somehow generate hardware descriptions. If this were possible, this would enable rapid design space exploration, not just coming up with one design point, but you could explore multiple design points, and could provide a baseline for performance evaluation on an FPGA implementation and then ASIC implementation. So at the bottom, you see this. You start with a reference C code, but the catch is you have to modify this reference C code into a subset C, which is HLS-ready, and then pass it through a HLS tool. For example, we used Vivado high-level synthesis tool, and then we optimized this generated RTL. We could have Verilog, but we did, I think, Verilog, and we mapped it both to an FPGA and an ASIC. So given the reference C code, modifying it to be HLS-ready C code required a few things. For example, regular C code has library functions. Regular C code has recursion. Regular C code supports dynamic memory allocation, file operations, and so on and so forth. And none of these C constructs have a hardware equivalent. And so you have to take each of those C constructs in each of those reference code that was provided and rewrite them so that these are statically with equivalent codes that are HLS friendly. And we'll see what they are. So that was the process we embarked upon. And we thought this would be straightforward. We thought it would take about a month, but it dragged on to over about a year. And it was painfully hard. So the PhD student, Deepak Soni, led this effort. He's now at Apple. He graduated. And the postdoc was Kanad Basu, who then moved on to UT Dallas, and now he's an tenured associate professor at RPI. So the pipeline looked something like this. Start with a C code, make it HLS-ready C code, then run it through HLS.
Ramesh, I don't think we see your slides.
You don't see my slides. Did you see any of the slides or no? Did you at some point see the slides, Warren?
Early on.
Okay, let me stop sharing. And let's me start sharing again. Share.
There we go.
Now?
Yes.
Okay, good. Thank you for reminding. So this is the C2 silicon pipeline. One on the left, you see the FPGA pipeline, and the other one is the ASIC flow. So you start with the standard C, convert into HLS-ready C, and then use Vivado HLS to map it to convert this C to RTL. And then you apply optimizations like loop unrolling and loop pipelining to explore the trade space between latency and area. And while you make these changes, you also can do C to RTL co-simulation against the known answer tests that are provided at the time of submission for the NIST competition. So we used Arctic 7 FPGA as the Xilinx target. And on the right-hand side, we have the ASIC synthesis flow goes through something similar, but we targeted the global Foundry 65 nanometer standard cell library to report the results. Okay. So in retrospect, all of this looks straightforward, but let me tell you what the difficulties were. Before I get there, let's talk about the various candidates that we evaluated. I said we'll look at 9 candidates, but at some point we gave up on the 9th one and we focused on 8 of these 26 candidates from round 2 of the NIST PQC competition. And these were the 8 candidates, 3 lattice-based, 3 multivariate-based, and 2 hash-based algorithms. So we applied this methodology and it worked, but it was painfully hard. So once you have this flow, immediately you can do lots of trade space studies. For example, Falcon in our study, this was about 4 or 5 years ago, demonstrated the fastest signature verification. Power efficiency wise, Falcon and Dilithium were very good. Q Tesla was more complex. And the problem with Falcon was its key generation step involved floating point operations. And so we did not implement that piece of it. Okay, this is using signature verification. Using the target was a GF65 nanometer ASIC library. Okay. So if you look at the various algorithms, the primary kernels that consume area are hash functions typically and polynomial multiplications. These are most, and they show up in as different functions in different algorithms. So what one should do, so the initial trade-off, as I said, the initial goal was to make sure that all the C code was made HLS ready. We didn't do too many optimizations, but we opened up the resulting synthesizable C code. And a variety of functions that could be optimized. And as I pointed out, hash and polynomial multiplications are the things that potentially need the optimization. And lots of work has gone on independently. Those that have written Verilog code, direct RTL, many more optimizations. There is the Athena project at GMU that systematically does some of these trade space studies, and they have gotten involved in some of the studies as well. So I just wanted to give you the timeline that we were working with. We wanted to report some initial results by the time to inform the standardization process. So this is what we did. This work yielded a foundational benchmark, demonstrated a uniform methodology, which is take C, convert it to synthesizable C, and go through the repeatable HLS-based flow using Vivado HLS as the high-level synthesis tool to compare these cryptographic schemes. And we provided some initial baseline hardware performance data for the signature schemes that I discussed, mapping them onto an FPGA and onto an ASIC platform. And this C code is accessible for those of you who want to use this. You can just click on that link and you will have access to that data, and it's open for the researchers. So this was circa 2021 or so, I would say. And we stopped working on this topic because my student and the postdoc moved on and others weren't interested in picking this up. Okay, that was part one of the story. So fast forward, I think about 2 years ago, 2024, I think, or late 2023, we started revisiting high-level synthesis using LLMs as a way. I call it higher level synthesis, where LLMs could be used to translate English language specifications into synthesizable C and so on. And then we also added on additional capabilities so that we could make it as an agentic framework using regular chat-based models and reasoning models. And I'll talk about that now. And this has nothing to do with PQC. So in parallel on a different path, along a different path, we were focusing just high-level synthesis. So as I said, the challenge that we picked up was to bridge software and hardware implementations. So what we wanted to do is see if LLMs or Gen AI agents act as translators from regular C to synthesizable C, and as system architects that can automate the search for optimal instructions to the high-level synthesis tool. And these instructions are called pragmas, so as to balance performance with area and power consumption. And instead of making the LLMs generate the results, what we ask the LLMs or Gen AI tools to do is to actually formulate these problems, these system architects problems, as integer linear programs and bring in ILP solvers to solve those, because ILP solvers are quite good at some of these architects roles. So we decided not to use LLMs to do this solve this problem, but just to translate them into ILP language, whatever was the language for that particular ILP solver was. So this was the goal of that particular effort. And this is ongoing, and many more changes have happened, many more improvements have happened, and I'll talk about that as well. So there were two steps here, two tasks. One of the first things, as I mentioned in the early part of my talk, is was we converted C code into synthesizable C by going through each kernel at a time. So we did the same thing even here. So at the kernel level, optimizations included inserting loop unrolling, pragmas, and other pragmas as well, typical HLS pragmas. So the typical feedback loop that if you had the human, you would have done the same thing, but here it is the LLM in the loop. LLM generates a particular instance of this with set of pragmas, and the compiler checks if there's any errors, and that error feedback is sent back to the LLM, and that loop iterates. And once there are no more compiler errors, you go back to the HLS, go to the HLS and go through a similar loop to make sure that HLS-ready C code is indeed HLS-ready, and then run it through HLS, at which point all these pragmas are activated. So that is the task one, which is on the top right here, on the left-hand side at the top. And you do this for variety of kernels, and you come up with these pragma insertion. And the study. So now you have a bunch of kernels that are part of a larger system. And now you want to study or put on the hat of a system architect to see which kernels, which pragmas to trigger and which pragmas not to trigger, right? This is the Pareto frontier study, trade-off study, trade space study, and so on. So as I mentioned, the task two here is full system optimization. So here the agent optimizes the whole application architecture, not the individual kernel level optimizations. So here the tool inspects the kernel, formulates the ILP, throws it across to an ILP solver to solve the ILP, get the solution, integrate it with the rest of the solutions, and study the overall area performance trade-off. Okay, so that was the second task within this HLS agentic framework. So as I said, this was unrelated to PQC at this point in time. So we looked at a couple of things. We studied the language models at that point in time. DeepSeek just came about. So we started looking at the standard DeepSeek model and the reasoning-based DeepSeek model and OpenAI O3 Mini, which is also, I think, is a reasoning model that emitted reasoning traces and so on. The intuition here is that these reasoning models potentially mimic human thought process, chain of thought, and problem-solving process, and so on. You have much better reasoning models now, and if you look at those, you will see that the intermediate steps are similar to what you would do. So I play with Cloud, ChatGPT, the more recent reasoning model. They are pretty good at the reasoning of what steps to take and what steps not to take, and so on. So what we did then is to use this setup and run variety of benchmarks. We created a few synthetic designs to support various data dependencies. That is, imagine to dependencies like parallelism and sequential dependencies. And 6 real-world designs, including AES, SHA-256, and a few others. The papers have more detail, but this is the C to HLS C paper. I think it's part of it appeared at today's journal. And we looked at these metrics. Are the codes compilable? That's one of the success rates. what is the cost of using these Gen AI agentic frameworks? So we count tokens as a proxy, number of tokens consumed as a proxy for the cost of doing these designs. And quality is in terms of the area of the design and the performance, which is the latency of the design. So these are the kinds of studies we did. And the paper has lots of these studies, experiments, and so on. So I don't want to go through all of those. And I wanted to keep this first talk reasonably high level. So a few things. This is, again, 2 years ago. The reasoning models are quite stable and do quite well. The reason ones do quite well. The reasoning models did quite well, most very reliable. DeepSeek, the chat model at that point in time, had the lowest lowest success rate. In fact, on AES, it was about 40%. And the cost is shown on the left-hand side, the number of tokens consumed and the cost of that. So as probably this is not counterintuitive. Reasoning models cost more. Yeah, so they do well, but at a significant premium. And we have studied other things of whether you want to bring in chat models, the cheaper versions initially, and when they fail, bring in the switch over to the reasoning models. Those kinds of trade-offs could be done as well. So this is in terms of the design exploration, the framework, and so on. So a couple of things we found. Is this the physics gap? What these tools, the reasoning models, still fail to capture is the parallelism that is inherent in hardware, right? They confuse software sequential operations with hardware parallelism. So they struggle to formulate some of these ILP, integer linear program constraints for latency. So reasoning models fail to do that. The other model, which is the chat model, just does brute force and succeeds well. So this was about a year and change ago. For example, when you see the latency, it should be max of A and B if they're not dependent. If A and B are two operations that are not dependent, then you could see the latency between them as the max. And if they are dependent on each other, it should be the sum of the latency of A and sum of the latency of B. So even these simple inferences were not the tools or the agents were making these mistakes. So that was one thing we found, but by now probably some of these are solved as well. So we were able to automate, start with the higher level, which is English specification, and convert into C, or start with regular C and convert into synthesizable C. And this agentic framework could formulate ILP, ILP models. They could insert pragmas, and they could support automatic verification without human in the loop using the known answer tests, for example, for PQC or any test vectors or unit tests that you provide for the kernels that are being run through the HLS loop. And I talked about the shortcomings of DeepSeek and so on. And on the third hand, on the third bullet is something like this. If you look at general C code, sometimes you have all these memory allocation statements. Sometimes you don't pre-compute constants, you compute constants on the fly. And these are all things that regular HLS doesn't support. So you may have to pre-process them, and that specialized pre-processing is something that these tools can do. And see, so this is where we focused on for the last year and change on just agentic framework for high-level synthesis. So in 2021, we looked at PQC started changing by hand or manually altering the regular C to synthesizable C, and here we are able to automate it. So bringing them together over the last few, so this is, I think, this is one of the papers that appeared at one of the conferences, and a follow-on paper appeared at a ACM Transactions on Design Automation. So we wanted to bring these two together, the PQC, post-quantum cryptography, and agentic or LLM-based high-level synthesis, and also bring in security all into the mix and see what we can do with that. And this is ongoing work, so you will see even less detail, but we have some a couple of papers that have come out. So just a quick cartoon summary of what I talked about. Given a C code, LLM agent generates HLS C. Here, since more recently we started using Catapult instead of Vivado, so we use the HLS compiler from Catapult, and you get both errors and PPA metrics, and those can be used by the LLM agent to regenerate the HLS C, right? So the manual translation that I talked about early on has been replaced by the LLM loop. So there is no more manual translation in this. And the LLM can iteratively refactor software-centric C code and run HLS compilation and take the out and simulations, RTL simulations, and take those errors, feedback into the agent for corrective prompts and so on. So the goal was to automate this C to HLS C process, and also to insert pragmas, and also to study the design space of area versus latency versus power without human intervention. That is the aspirational goal. We are getting there. We are not there yet. And the next thing is to make sure that the designs that come out are comparable to handwritten RTL. And we haven't even touched that piece of the puzzle. So here we have about 4 steps. The first step or the first phase is to identify critical kernels while preserving the functional interfaces, and generate unit tests for those identified and isolated kernels from the initial input-output known answer tests from the PQC subroutines for the particular standard, right? Then you do a couple of things. Change any of these runtime table initiation to compile time array creation, so that the HLS tools can infer the size of ROM or RAM, whatever is needed. Similarly, take this dynamic mallocs, dynamic memory allocation, and rewrite them into static arrays, and other tricks like remove recursions if there are any, and so on and so forth. So that is the pre-processing step 2. Notice that these were done by hand when we were doing meeting that stringent schedule for the NIST competition. But we could do this over the last 2-3 months. We are not there fully done with all the algorithms, but the framework is ready, and we are rewriting the framework. So once we had this once the HLS pre-processing is done, you get the HLS-ready C, and then we could do this design space exploration, including inserting of pragmas and studying the area latency trade-offs, right? And finally, we do C to HLS, C to RTL co-verification using the known answer test. The benefit of using PQC and other cryptographic algorithms is they have a comprehensive suite of tests known as KATs, whether you go to PQC or whether you go to any standardization process, they have all these CATs, which are very useful that you're not writing, but can be used to generate an FPGA targeted implementation target that targets an FPGA or an ASIC. So this is the four-step process we formulated. And so as I said, a couple of examples. If you have a malloc, something like this, you change it to something with a fixed array bound, because that's when hardware is fixed. It's not dynamic. You cannot create memory on the fly. What you could you can pretend doing that when you write it in software, but in hardware, the memory is fixed. So that's one translation you have to do. Similarly, you could do this if you look at this FFT, the twiddle factors in the NTT algorithm, some codes have this being done on the fly, but you can pre-compute them and create a fixed twiddle ROM, for example. These are the kinds of translations that the LLM preprocessor does, and other things, other stuff like this can be done by LLMs. And you check every time you make a change, you check it against the known answer test. And that used to be the most time-consuming part for us when we were doing this about 4 years ago. The student and the postdoc and others used to make the changes and rerun these tests and find a mistake and start debugging. Whereas with these LLMs, you could literally automate away that process. So that was a huge performance gain in terms of designer time. So we studied the variety of these things, efficiency, complexity, design space exploration. Whatever we did using by hand, we could do this using these automated tools. So even more recently, I think about over the last 1 month or so, we started looking at the security aspects of such of these codes, of PQC codes. For example, we focused on looking into the side channel leakage of the generated designs, right? What are side channels? For those of you, there are the power side channel could sometimes power timing and other side channels could leak the secret, any secret dependent information that the algorithm runs or executes on the hardware by just monitoring the outputs, the power consumption as the algorithm is executing on the stuff. So we said, can we look at this code? And besides performance and power and area, can we also look at the security aspects of the generated C or the resulting RTL, one or the other? So what we did is we took one kernel, NTT, which is part of Kyber, one of the PQC algorithms, and came up with 3 variants. Variant 1 was removed all data-dependent branching. So if you look at C code, they have some conditionals and so on, C code that, so you could rewrite those C codes to eliminate data-dependent branching. That was one variant we asked the LLM to create. Similarly, we did something called masking and shuffling, second variant. And the third variant, we suggested using what's called a constant time polynomial reduction using a Barrett technique. Barrett is the author of the technique. So asked the LLMs to rewrite the code, or prompted the LLMs to rewrite the baseline code to support variant 1, variant 2, variant 3. And every time we made these changes, went through all these verification and validation steps. And you see the benefit of these AI or the agentic frameworks where you don't have, as a designer, don't have to sit and debug and figure out all of these all of these steps. You could literally let them do it and check the final results. Hypothetical. This is, again, an aspirational goal. So this is what I did. I think I took about a half hour. We started with the manual era, is what I call it, in 2021. The students, we handcrafted some of the groups around the world handcrafted RTL, and we took the C code and handcrafted the synthesizable C. Even that was painful. And we did the optimizations, or studied the optimizations. And as I mentioned here, months of engineering, human engineering time was invested. So in the phase 2 LLM era, we used LLMs as part of an iterative loop that have the C compilers, HLS compilers, so on. So it reduced the efforts significantly, and the focus is still functional, making sure it's functionally correct and it's synthesizable, and then inserts the kinds of pragmas and does the design space exploration as needed. And more recently, we've been looking into adding on various agents that support security. One of the first ones that we looked at is the power side channel resilience. So we're trying to automate as much as possible using some of these current and emerging AI, Gen AI frameworks. So on that note, I'll pause here, take any questions, and thank you for joining us. Any questions? Otherwise, we can. Thank you. If there's no more questions, you can drop off as well. And that's all. So I'll end this conversation. Bye. Thanks.